The recent revelation that NASA has quietly refined the trajectory of the interstellar comet known as 3I/Atlas has introduced a new layer of uncertainty into what was previously considered a relatively straightforward celestial flyby. While the adjustment may appear subtle on paper, involving only a slight recalculation of the comet's projected path, the implications of this change have sparked intense discussion among astronomers and planetary scientists. At the heart of the concern is the comet's upcoming close encounter with Jupiter, scheduled for March 16, 2026, and the fact that revised models now place the object skimming just outside the giant planet's gravitational Hill sphere. This boundary, while invisible, represents a critical threshold in celestial mechanics, and crossing it, even marginally, can mean the difference between a harmless pass-through and a gravitational interaction with potentially far-reaching consequences. 3I/Atlas is no ordinary comet. Discovered in July 2025, it was quickly identified as an interstellar object, only the third of its kind ever observed passing through our solar system. Unlike comets that originate in the distant Oort cloud or Kuiper belt, interstellar objects are visitors from beyond the Sun's gravitational domain, remnants of other planetary systems that were ejected into deep space long before our own solar system took its current form. The hyperbolic trajectory of 3I/Atlas confirmed that it is not bound to the Sun and that, after its brief journey through our planetary neighborhood, it will eventually disappear back into interstellar space, likely never to be seen again. When 3I/Atlas first entered the inner solar system, its behavior seemed largely unremarkable. In October 2025, it made its closest approach to the Sun at a distance of approximately 1. For astronomical units, safely beyond Earth's orbit. Observations during this period suggested a relatively typical cometary structure, with a developing coma and tail driven by solar heating. There were no dramatic outbursts or unexpected deviations, and early orbital projections indicated that its future path would remain well clear of any major gravitational entanglements. In particular, scientists believed its encounter with Jupiter would occur comfortably outside the planet's Hill sphere, ensuring that Jupiter's immense gravity would not significantly influence the comet's motion. The Hill sphere itself is a concept that plays a central role in understanding why this revised trajectory has caused such unease. In simple terms, the Hill sphere defines the region around a planet where its gravity dominates over that of the Sun. For Jupiter, the largest planet in the solar system, this region is enormous, extending millions of kilometers into space. Objects that pass within this zone can experience strong gravitational effects, including deflection, acceleration, or in some cases even temporary or permanent capture. Staying outside the Hill sphere usually means that an object's path will be only mildly perturbed, if at all, by the planet's presence. What has changed, according to recent analyses shared by astronomers on social media and in preliminary reports, is that 3I/Atlas's predicted closest approach to Jupiter now lies perilously close to this boundary. Rather than passing comfortably beyond the Hill radius, the comet is expected to skim just outside it, with the margin separating the two being extraordinarily small on cosmic scales. This razor-thin difference is enough to matter because gravitational influence does not end abruptly at the Hill sphere's edge. Instead, it fades gradually, meaning that even a near miss can result in measurable effects on an object's velocity, rotation, or physical structure. The source of this revised trajectory lies in newly refined orbital data, made possible by observations that go far beyond what ground-based telescopes alone can achieve. As 3I/Atlas passed relatively close to Mars, a fleet of European and American spacecraft orbiting the red planet were able to capture detailed images of the comet against the background of space. By triangulating these observations from multiple vantage points, astronomers significantly reduced uncertainties in the comet's position and motion. This level of precision allowed for a more accurate reconstruction of its orbit, revealing the slight but crucial deviation toward Jupiter's domain. Such refinements are a normal part of orbital science, particularly for newly discovered objects whose trajectories are initially based on limited data. However, in this case, the improvement in accuracy has transformed what was once considered a non-event into a scenario that demands closer scrutiny. Even a tiny change in velocity or direction, accumulated over millions of kilometers, can shift the geometry of a planetary encounter in meaningful ways. For 3I/Atlas, that shift has brought it to the very edge of Jupiter's gravitational reach at precisely the wrong, or perhaps most interesting, moment. The potential consequences of this near-Hill sphere encounter are varied and still the subject of debate. One possibility is that Jupiter's gravity could slightly alter the comet's hyperbolic trajectory, changing its speed or exit direction as it leaves the solar system. While such a change would not threaten the stability of a solar system, it could affect scientists' ability to trace the comet's origin or predict its future path through interstellar space. More intriguingly, a close gravitational interaction could influence the comet's physical behavior, particularly its outgassing and tail formation. Gravitational stresses, combined with tidal forces, might trigger changes in how volatile materials sublimate from the comet's surface, potentially leading to unexpected activity or fragmentation. Some researchers have also noted that Jupiter has a long history of dramatically reshaping the paths of comets. Often referred to as the solar system's gravitational gatekeeper, Jupiter's immense mass has both shielded the inner planets from frequent impacts and, paradoxically, redirected countless objects into new orbits. Famous examples include Comet Shoemaker, Levy 9, which was captured by Jupiter's gravity and ultimately torn apart before colliding with the planet in 1994. While 3I/Atlas is not expected to come anywhere near that level of interaction, the historical precedent underscores why scientists are taking even a marginal approach so seriously. Despite the heightened attention, most experts emphasize that there is no immediate cause for alarm. The phrase unexpected consequences refers more to scientific uncertainty than to any existential threat. The solar system has endured countless flybys by comets and interstellar objects without incident, and the laws of gravity are well understood. Nonetheless, interstellar visitors like 3I/Atlas are rare, and each one offers a unique opportunity to test models of celestial dynamics under conditions that cannot be replicated by solar system-borne objects alone. Any deviation from predicted behavior, no matter how small, is therefore of immense interest. In the coming months, astronomers will continue to monitor 3I/Atlas closely, refining its orbit further as new observations become available. As it moves farther from the Sun and closer to Jupiter's orbit, additional data will help determine whether the comet's path remains just outside the Hill sphere or drifts slightly inward. Even a minuscule adjustment could tip the balance, turning a near miss into a mild gravitational encounter. Space agencies and observatories around the world are expected to coordinate their efforts, recognizing that this fleeting visitor represents a once-in-a-generation chance to study the interaction between an interstellar object and the solar system's largest planet. Ultimately, the story of 3I/Atlas is a reminder of how dynamic and interconnected the solar system truly is. What begins as a small update to an orbital calculation can ripple outward, prompting new questions about gravity, planetary influence, and the behavior of objects born around distant stars. Whether the comet ultimately slips past Jupiter unchanged or experiences a subtle but measurable gravitational nudge, the data gathered from this event will enrich our understanding of both interstellar visitors and the powerful forces that shape their journeys. In that sense, the real significance of this revised trajectory lies not in the risk it poses, but in the scientific insight it promises to deliver.